No. 95.
Permanent and hits. Yeah. 104.
Yes. 92.
And 107? Okay.
And that is it.
Yeah, one's a miss.
So
See,
now,
I'm not doing it, boss.
so you have 1 4 left, right?
About 3 minutes.
17.
Let's see.
Participate.
What, bro, what do you?
40. 17.
Our guy, 18.
Go.
What you do? 43.
No. Number
This.
59.
Really?
Guys.
Well, you already did 50.
Oh.
You already did 59.
You did?
Yeah.
Number.
Okay, yeah.
69.
You're going to 53? Yeah. Hit.
You know how to speak? Yes.
Exactly.
You don't want to wrap up?
38.
Wrap up on the county like you found.
And I just didn't do that.
Oh, I know what you want.
My skills are 17.
How much? Yes.
Yes.
What?
85. Go. And where you are. Boom, I shot. And done.
Well, I won.
You're gonna give less.
Sure, where do you think I was?
71, 103.
Oh.
Cheater! Wow, wait, what?
Well, that's your fault.
Who's undefeated? Anybody undefeated? Probably not.
You did all that on your book. Oh, wow.
Impressive.
Yeah, I did.
How's the foot, Ridley? Doing okay? Hurt too bad or no? Yeah, that's usually it. You just gotta watch how you move it. Have a girl. Grab them up.
Oh, I think that worked for you. I don't want the hello. Continuing the legacy. No, it's the.
If you want, really, I can get you a folding chair that is comfortable. Would that be comfortable? Or are you comfortable like that?
It's we need to make fast.
I don't just. That is why. It's hard. Organized. I may or may not have stolen Xander's binder.
Oh, okay, it happens. We steal things from time to time. So Ridley, my mom used to be a My mom used to be a 911 dispatcher. When you go to get hired for that job, sorry, they send you for a polygraph, so a lie detector test is part of the process. So one of the questions they asked her is, have you ever stolen anything? And she immediately replied, no, yes, I steal pens. I steal people's pens all the time. She's gonna get in trouble. Cause you know it. She's like, oh no, I just said no to the lie detector when I have stolen things. Cause you know, like people used to write checks for groceries and you know, people would hand you a pen at the checkout and you'd put it in your purse and walk out with it, you know. It's like, no, I steal pens. It's funny. Yeah, accidentally. I actually I walked out of Walmart with something in my cart once that I didn't pay for. And then the next time I went, I just like randomly grabbed the same thing off the shelf and told the cashier, I was like, I need you to ring this up and then put it back. Cause last week I accidentally stole it. Like it felt real bad.
I still keep my best friend and then never intend to give them back.
Oh.
They work better with my outfit.
There you go. That happens. That's a thing. Mhm.
There's a way to bypass lie detectors.
They're not even admissible in court. They're not great.
I was like, make another stress and then I get
You can take certain medications. There's all kinds of things you can do. That's why they're not admissible.
I've stolen rubber bands.
But in the 80s, they gave them to everybody for everything. So, all right, anybody undefeated?
Yeah.
All right. Okay, we got a couple of battleship gurus in the room.
Andrew.
Admirals, shall we say?
Andrew. You only play like one match.
All right, well, let's go ahead and get started. So today we are talking more about elements, properties, how the periodic table works. So in the early 1800s, we had this dude, Johann Dobereiner. That's a great name. So he attempted to classify several elements according to their properties. All right, so this is pre-Mendeleev, but we're giving it a shot. And he noticed certain groups of 3 elements had certain properties. And he noticed that the mass of the middle element was approximately the average of the mass of the other 2 elements. And what he called this pattern? Anybody know? Anybody see? Do you remember?
Yeah.
No, he called his pattern the law of triads. So what he's saying is the mass of boron is roughly 10.8 and the mass of nitrogen is roughly 14.0. We took that average, we'd get about 12. And okay, I'm seeing a pattern. So he called it law of triads. So you have tri in there, so it's 3, right? He's working with elements in groups of 3. So he's a cool German dude, and he looks rather chill with his circa 2012 Justin Bieber hair and things smoking on the table in front of him. So you can remember Dobereiner for the Bieber hair and the smoking items and the law of triads. So for example, if you look here, so iron, cobalt, nickel, you have about 51, you have about 59. And in the middle here, 56, 59, which puts you at about 58 when you average them out. So this is the kind of thing he's seeing. So these are some of the groups of triads that he noticed. And he also noticed that they don't just go horizontally in periods, now that we call those periods, but they also kind of work in groups. They work vertically too. So for example, he did chlorine, bromine, iodine right here. And he saw the same kind of pattern that this one and this one kind of averaged this one. Oh, all right. So he's noticing something. So this is good, but we still have very little organization yet. So after him, we get this guy. This is Newlands. Now, Newlands is the guy that Mendeleev worked off of. He used Newlands' findings to kind of inspire what he did, which was building our table the way closer to the way we see it now. So in 1865, this guy, Newlands, arranged the known elements by property and by order of increasing atomic mass. And he noticed that the patterns are repeated about every 8 elements instead of every 3 elements. So what did he call this? Do we know? Anybody? So he called this the law of octaves. All right. So he's an English dude. He's got an awesome beard and he would fit right in with your modern day hipsters, wouldn't he? Like this looks like a guy you could find in Midtown. or, you know, Cabbagetown, Atlanta. He'd be hanging out in, yeah. You're probably right, unfortunately. Yeah, he looks, yeah, very hipsterish, I'd say. So these are the octaves that he saw. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So he's like, okay, I'm seeing patterns where these things work off each other again. All right, so we're getting somewhere. All right, still not quite what we need yet, but we're getting somewhere. So interestingly, both triad and octave are musical terms, oddly enough. So your triad is your chord made up of 3 tones called chord factors or diatonic, if anybody's music here. So we call that the root, the third, and the fifth. And they're your tonal harmonies that look like this. They're your 1, 3, 5s, your C, E, G, that kind of thing. And then your octaves are, of course, an interval that's a full octave above, which is 8 notes, which means your frequency is going to be twice that of your lower notes. So last year when we did frequency, we talked about sound waves and frequency. Notes that are an octave apart are exactly, the higher one is exactly twice the frequency of the lower one. So that means, so are we paying attention here? That means that your A above middle C, which is where most orchestras tune, is 440. There's actually a whole thing about whether you tune to 440 or 440 and just a little change. It's a whole thing. We could get into that. But if your A above middle C is at 440, then your A above that, where is that going to vibrate? Your octave above it is going to be double. And then the one below it is going to be at how many hertz? 220. Yep, there you go. All right. So Newland's octaves looked a bit like musical octaves. It kind of fell in like that. So this is where he was going. But he had some problem. And his problems were the transition metals here, transition elements. So those ones in red didn't fit his pattern. And he couldn't figure out why. So then we get to our buddy.
Oh, wow. Yeah.
Ah, this is Mendeleev, right? Okay. So 1865 Mendeleev. All right. Next week, you're getting next lab you're going to be doing is you're going to be using the same processes that Mendeleev used to fill out his table to find some mystery elements within your table that you're going to have based on the same properties that he was using. So Mendeleev took Newland's idea and then he expanded on it. He placed the symbol, characteristics, and atomic mass of each element on a card, physical cards, okay, and started moving them around. How can I make this work? So when he was teaching inorganic chemistry, so what's organic chemistry versus inorganic chemistry? Does anybody know that one? Do you know?
Organic is organic, inorganic is inorganic.
Yeah, that's right. So organic chemistry has to do with molecules that contain carbon and come from living things. Okay. So he could not find a textbook that was meeting his needs because he was real picky about what was in it and nothing had been written yet. But he'd already written a book in 1861 that won him a prize called the Demidov Prize. And he set out to write himself another book. So the result was this one called Osnovy Chemii, which is Principles of Chemistry in Russian. And it became a classic. This was the book, the chemistry book. And it went on for many editions and in many translations. And it was when he started to write the chapter on the halogens. So that's chlorine and its analogs. So these guys right in here, these are halogens. When he started to write the chapter on the halogens, he compared the properties of this group of elements to those from the group of alkali metals, which are these guys over here. Okay, kind of the reddish orange color. And what he found was that the elements are dissimilar, but there were similarities in the progression of their atomic weights or masses. And that allowed him to kind of think differently than anybody else had been thinking so far. So he wondered if they exhibited similar properties. So after studying those alkali metals, those guys on that end, Mendeleev established that the order of atomic weights or masses could be used not only to arrange the elements within each group, but also to arrange the groups themselves. So this was an effort to make sense of it, what everybody else had come up with so far. And that's how he discovered what we call periodic law. Period meaning repeats at a regular interval. So that's what we see here is a pattern that repeats at a regular interval. So he's a cool Russian dude. He's one of my favorite guys, and we have some fun stuff about him too. So we'll come to that in a minute. But his first tables, they look like this. So first off, they're in Cyrillic. So unless you can read Cyrillic, which is the Russian alphabet, good luck. I cannot read Cyrillic. But that's where he started. That doesn't look like this, right? It's not even close. But it was the basis for it. So he gets credited with the modern periodic table, even though his table didn't really look like this. But he got us started on that road. All right. If it will go. Why doesn't it want to go? Oh, there it goes. All righty.
Oh, it's a car ad.
We got a car ad. Gotta love car ads. At least it's not politics this week. Ooh, yeah. Let's drive whatever that is. Oh, it's a BMW. It'll break down every 4 days. There you go. All right, there you go. No Trump ad today. That's really nice. Grateful.
Periodic table is instantly recognizable. It's not just in every chemistry lab worldwide. It's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon. It's a massive slab of human genius, up there with the Taj Mahal, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitry Mendeleev, is a bona fide Science Hall of Famer. But what? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really. That had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their two-letter symbols arranged in a table. Check out the entry at the third column, fifth row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. That dash is science. By putting that dash there, Dmitry was making a bold statement. He said, and I'm paraphrasing here, y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka aluminum. Eka being Sanskrit for one. Nobody's found Eka aluminum yet, so we don't know anything about it, right? Wrong. Based on where it's located, I can tell you all about it. First of all, an atom of Eka aluminum has an atomic weight of 68, about 68 times heavier than a hydrogen atom. When Eka aluminum is isolated, you'll see it's a solid metal at room temperature. It's shiny, it conducts heat really well, it can be flattened into a sheet, stretched into a wire, but its melting point is low, like freakishly low. Oh, and a cubic centimeter of it will weigh 6 grams. Mendeleev could predict all of these things simply from where the blank spot was and his understanding of how the elements surrounding it behaved. A few years after this prediction, a French guy named Paul-Émile Lecoq de Bois-Baudran discovered a new element in ore samples and named it gallium after Gaul, the historical name for France. Gallium is one step away from aluminum on the periodic table. It's Eka aluminum. So were Mendeleev's predictions right? Gallium's atomic weight is 69.72. A cubic centimeter of it weighs 5.9 grams. It's a solid metal at room temperature, but it melts at a paltry 30 degrees Celsius, 85 degrees Fahrenheit. It melts in your mouth and in your hand. Not only did Mendeleev completely nail gallium, he predicted other elements that were unknown at the time: scandium, germanium, rhenium. The element he called ekamanganese is now called technetium. Technetium is so rare it couldn't be isolated until it was synthesized in a cyclotron in 1937, almost 70 years after Dmitry predicted its existence, 30 years after he died. Dmitry died without a Nobel Prize in 1907, but he wound up receiving a much more exclusive honor. In 1955, scientists at UC Berkeley successfully created 17 atoms of a previously undiscovered element. This element filled an empty spot in the periodic table at number 101 and was officially named Mendelevium in 1963. There have been well over 800 Nobel Prize winners, but only 15 scientists have an element named after them. So the next time you stare at a periodic table, whether it's on the wall of a university classroom or on a $5 coffee mug, Dmitry Mendeleev, the architect of the periodic table, will be staring back.
So he was able to tell what was missing based on the properties. He'd know there's an element missing here, and here are its properties. That's going to be your next lab. Your next lab is going to be essentially doing exactly what he did. Like, there's something missing. Now, if you find it, how do you know that it belongs in this particular spot? So yeah, it's fun to kind of look and see which ones are named after scientists. Here's another one nearby, Einsteinium, right? So what's not to love about this dude? Okay, we're gonna start with some fun Mendeleev quotes. All right, this guy had some good stuff. So I like this one. The establishment of a law, moreover, does not take place when the first thought of it takes form, or even when the significance is recognized. It's only when it's been confirmed by the results of experiment. Do we agree with that today? Is that kind of our definition of scientific law? Kinda, pretty close. I like this one a lot. Take this one to heart. Work. Look for peace and calm in work. You will find it nowhere else. This is also very Russian, right? Work, 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 and you'll find your peace. This is a very good point. Find a vocation that you love, that you find peace and calm and you find value in, and you'll be happy. You know, whatever your vocation is, if it makes you happy, you'll be happy. That's an important point. There is no talent, neither genius without hard work. Again, he's reminding you that he's Russian, right? Oh yeah. Uh-huh. The most all-penetrating spirit before which will open the possibility of tilting not tables but planets is the spirit of free human inquiry. Believe only in that. He's going to end it very seriously. Believe only in that. There's a directive for you. Okay. But dude, this dude's eyes. All right. Y'all notice this, right? You've looked at like 8 or 9 pictures of him now so far. This is the kindest, gentlest picture of him I could find. This is the one you see a lot. All right. And this has led to fabulous Mendeleev memes. Go looking. You will find them. For example, my favorite element, surprise, stabs interviewer. There's a lot of that with Mendeleev. The dude looks like he's ready to take you out. I mean, doesn't he?
Yeah.
What's with the eyes? That would make him even, I don't know. Ugh. And he was a fairly substantial guy. Like, he's a bigger guy, you know? It's like, geez, man. So, but seriously. So this is interesting. So in 1850, this man walked 1,000 miles. I'll say that again. In 1850, he walked 1,000 miles. All right. Your shoes in 1850 are not the sneaks you're wearing today. I promise you, walking 1,000 miles is quite different than it even is now. So he did that so he could apply to the University of Moscow. And they said, no, sorry. Hope you enjoyed your walk. We don't want you. So then he walked to St. Petersburg, where they finally accepted him. And then that's where he got his table and eventually became this storied scientist. But his story is even more interesting. So there's some question about how many siblings he had. But in general, does anybody want to guess how many siblings Mendeleev had? 6? 16? 13? Most common answer is 17 siblings. And he was the baby. Okay, so he was the youngest of roughly 17. His brother Pavel said that about 14 of them stayed alive to be baptized. So they Russian Orthodox baptized as infants. So about 3 of them probably died shortly after birth, but 14 stayed alive long enough to be baptized. So that's a lot of siblings. So the exact number is still kind of in dispute. Now, this is where it gets interesting when you talk about the legacy you leave. All right, so in 1876, although he was already married, he became obsessed with this girl. Named Anna Ivanova Popova. And he began courting her. He's married, but he's courting her. He's flirting. He's like trying to win her over. And in 1881, he proposed to her, but he threatened tried and she refused.
What?
Marry me or I'll kill myself. Thank you. But I'm glad that she didn't let him kill himself because this is kind of important. But still, my word. But the problem was, she's like, okay, don't kill yourself. I'll marry you. So they get married. And they get married, but he's still not divorced from Lasheva, his first wife. So the Russian Orthodox Church looks at this and goes, excuse me, you're a bigamist. This is not okay. Now, in Russia, the Orthodox Church and the government were not separate entities. There's no separation of church and state necessarily going on. All right. So he's a bigamist technically for a month. His divorce was finalized about a month after he married Anna. So Lasheva's like, thanks so much. That was a time of my life. And so because of that, the church is going to require 7 years before they recognize his marriage, his new marriage to Anna, as lawful. So basically, he was a bigamist for like a month. And then for 7 years, he was questionably a bigamist, or at least he was with this woman he wasn't married to. And because of that caused so much controversy that he was not admitted to the Russian Academy of Sciences. Despite being one of the most famous scientists in the world, his own country was like, nope, you don't get to join because you got issues with women and we don't want you. And you're a bigamist and you're immoral and whatever, and you're not in. Yeah, right. So because of the link between the Russian Academy of Sciences, the government fixture there, the church fixture there, and his behavior, he did not get what should have been like kind of the standard elevation for him, right? Never got it. Probably also why we're not like dealing with a lot of other awards and things that he could have qualified for, because he was famous and everything else, but people are like, oh, tacky. We don't want you tacky. So our buddy Dimitri, here he is looking stressed, all right, thinking real hard. I don't know what this, yeah. Who am I going to stab today? Why am I chasing around a young girl while I'm married? My life is so complicated.
Stop yourself.
Here he is in bronze. Okay, the nose. Do you notice the nose? So you notice that the nose and the shoe are more polished. So what does that tell you? Do you know what that means? They're touching, right? Okay. So like there's a statue in this picture over here that was on this wall. It's Charles Bridge in Prague. And there is a statue on that bridge in Prague. And at the bottom corner of it is a little dog. And the little dog is that beautiful bronze color. And the rest of the statue is all patinaed. It's that dark color. And so we had to ask some people when my husband and I were there, we're like, why is everybody touching the dog? Because clearly people are petting the dog. It was just a little dog on the statue. Well, the dog belonged to St. John of Nepomuk, who was the bishop in Bohemia at the time. And he was the queen's confessor. So if she needed to confess, she went to him. And the king got real mad at the queen and then demanded that St. John of Nepomuk tell him, what has my wife been saying to you in confession? And he's a priest, so he goes, I can't tell you, man, it's confidential. And he goes, okay, I'm throwing you and your little dog into the river and drowning you, which he did. But people touched the dog because they believed the dog kept the bishop's secrets, so the dog will keep your secrets. So when you see things like this on statues, there's usually some reason that people are doing it. Now, in his case, there is a military academy nearby. And when the cadets are getting ready to graduate, they stroll past Mendeleev and they rub his nose and they keep going. That's what they do. It's their tradition to rub his nose before they graduate. So his nose is all shiny because a bunch of military cadets are stroking his schnoz when they go by. It's real weird, but that's what hey. And here he is in St. Petersburg today. So if you want to go find him,
why are you speech shiny too?
that's real easy to reach. So that sticks out. So people probably just put their hands on it when they go by. Yeah, there's less reason for the foot than the nose. So yeah, he is in St. Petersburg today. If you are looking for him, this is where you will find him. Yep. So anyway, there's our buddy Dimitri, one of the most storied scientists in all human history, reduced to what we all get reduced to. With a lovely hosta, I have to say, this is an absolutely beautiful hosta. It's in great shape. He's fertilizing it well, I suppose. So, hey, this is what happens. So Mendeleev's table was about 9/10 of the way there, but it needed one more important modification before it looked like that. All right. And that was the use of what as the organizing principle? So Mendeleev had been organizing by mass. What is it? Number. Okay. So what we did now is we go, all right, we are no longer going to organize by atomic number. We're getting atomic mass. We're going to go by atomic number. And atomic number is the number of what, everybody? Protons in an atom, right? The atomic mass is the protons and the neutrons together, right? Remember, we don't even add in the electrons, and it's the protons and the neutrons, but really it's the average number, the average mass of all the isotopes of that atom, which have, some of them have different types, different numbers of neutrons because they're isotopes. So that's where we get the atomic mass from. So that number can change, right? You can have a carbon that has one mass, and then you can have a carbon-14 that has a different mass. So organizing by mass, you can see, can be a little problematic because of isotopes. So he's like, oh, let's do it by number instead. Let's do it by protons, because protons never change. If you change the number of protons, you've changed the atom. If you change the number of neutrons, you have an isotope. If you change the number of electrons, you have an ion. So protons are the atom always. So he used atomic number instead. And this was Henry Moseley in 1913. Now Henry Moseley has, this is a sad situation, Henry Moseley. Well, Mendeleev was a little like, what? Moseley's sad. So Moseley did experiments. Anybody know what he was working with? So he was working with X-ray spectroscopy. And he showed he showed directly from their physics that cobalt and nickel have different atomic numbers, 27, 28, and that they're placed in the periodic table correctly by Moseley's objective measurements of their atomic numbers. Now, this is what's sad. He's a cool English dude, but he's got a tragic story. When World War I broke out, he resigned from his position at University of Manchester and joined the military because he thought, this is my duty. My country's at war. I'm young. I'm joining. So while serving in the field as a technical communications officer, he was shot in the head by a Turkish sniper. He was 27. 2 years after his contribution to science, gone. So had he not been shot in the head at 27 by a sniper, goodness knows what this man would have gone on to do with his life. Brilliant, brilliant man. So that's sad. Do what? World War I, Turkish sniper. It's like, what'd he do? He was British. That's all he did. He was just British. And he was a communications officer. So it's not even like he was like a sniper himself. He was just shot right in the head by a Turkish sniper. All right. So warning. I'm going to warn you. This video is patently ridiculous. But this is one of those where a teacher makes an assignment and says, you need to do this project. Okay. But it's actually informative, as goofy as it is. So this is a Henry Moseley biography by Hayden. What are Jaden and Kelvin? He's got a sciencey name.
Yo, Jaden, our chem project is due tomorrow and we haven't started.
Yeah, what should we do?
Let's just watch some TV.
Let's not. I'm guessing the teacher had a minimum length for your video.
Ew, it's a Discovery Channel. But wait, they're playing a biography all about Henry Moseley. Wait a moment, isn't that an atomic theorist that we could be presenting about for the chem project? Henry Moseley was born in 1887 and Weymouth, Henry Moseley grew up in a well-educated family, leading his family to enroll him into a private school. Sometime after, young Henry here thought all his lessons were too easy and began to study physics on his own. Henry, at the age of 19, was admitted into Oxford's Trinity College, where he eventually disappointed himself by graduating with second honors, not the first he had hoped for. In 1910, Rutherford takes Henry into his research group at University of Manchester, hearing that Henry is a very promising physicist. Rutherford is very happy with Henry's research and offers him a research fellowship, where Henry is more than happy to accept. The real science begins, Henry's scientific discoveries. In 1913, Henry Moseley created this ingenious invention, the X-ray spectrometer. With this, he used X-rays to analyze the properties of elements in a whole new perspective. Henry generated the characteristic X-rays of certain elements and began analyzing them. He would do so by placing elements he wants to investigate into an X-ray tube, shown in the example present. The elements are then sealed into the tube, like so. The two black wires then vacuum out all the air from the spectrometer. He made the use of the effect of energetic electrons when they hit to an element, causing creation of unique wavelengths. The wavelengths led to different reflection angles in the center of the spectrometer. The many wavelengths and reflections were unique to each element. These values allowed for calculations of the number of protons in each element. Henry discovers that the number of protons directly correlate to an atomic number. Henry rearranges the periodic table by atomic number rather than atomic mass, creating a whole new understanding of the periodic table. Suck my protons, Dimitri. What had happened to this promising young man, though? Well, Buddy Henry here thought it was his duty to serve in war and enlisted into the British Army when World War I broke out. Well, Henry got blasted in the face in 1906 and turns to Henry's great future.
These dudes.
Here lies Henry Moseley, the man who changed the world's knowledge on the periodic table, dying at the young age of 27. This marks the end of our documentary, The Life of Henry Moseley. Thank you for tuning in. Yo, Jaden, wake up. Let's just hand this documentary to Mr. Mo. He won't even know we just copied it.
Yeah.
Yeah. Okay. Yeah. Patently ridiculous, but a pretty decent biography with a surprising number of hits on YouTube.
They're just like, let's use as many different transitions.
Yes, let's try every slide transition we can use and weird animation where they go like this.
Let's use a squeegee.
Yeah, I don't know what was that.
Why did they record every sound effect in the video?
That's a great question. Oh, all right. So here's a good overview of the table.
All matter is built from 118 essential building blocks known as the elements, and throughout history, many people were set on a path of elemental discovery, while others attempted to create useful ways of organizing them. But it wasn't until 1869 that legendary Russian scientist Dmitry Mendeleev developed an elegant and very useful method, which would later evolve into one of science's most brilliant icons, the periodic table. The periodic table is a super organized collection containing information about each element placed into rows and columns. There are 18 numbered columns on the table that we call groups. These groups are sometimes referred to as families, and like real families, elements in a specific group share some characteristics. For example, elements in group 18 are called the noble gases. These are a collection of elements that are generally very unreactive, like helium and birthday balloons. Next door in group 17, aka the halogens, we find reactive elements that may bond with metals like sodium and potassium to make salts. But what is it that makes different elements share similar chemistry? It's all about the outermost electrons, or the valence electrons. Electrons within atoms are arranged in sets around the nucleus. The set of electrons that is furthest away from the nucleus is the one that interacts with the outermost sets of other atoms, and therefore mostly determines what kinds of chemical reaction that an element does or doesn't do. The periodic table groups elements into columns whose atoms have similar valence electron configurations, and therefore similar chemistry. In the case of the halogens in column 17, Each of the elements has 7 valence electrons. The noble gases in column 18 all have 8 valence electrons. Now let's take a look at the rows. Each row is called a period, and like the groups, each row is given a number, this time 1 through 7. Within each period, the valence electron configurations of the elements change from element to element since there are more electrons. As a result, we see the chemistry of the elements changing as well. Remember, a different number of valence electrons means a different chemical reactivity. For example, as we move across the second period, the strength with which an element's nucleus pulls on the element's electrons around it increases. Nuclei of elements on the left side of the table pull relatively weakly, so they are more likely to lose electrons in a chemical reaction. Nuclei of an element on the right pull much more strongly, so they are more likely to gain electrons in a chemical reaction. Periodic or repeating patterns of physical and chemical properties are crucial to the organization of the table. These patterns even allowed scientists in the past to predict the properties of as of yet undiscovered elements just by looking at gaps in the table. For example, let's take a look at Mendeleev's original 1869 periodic table. See this hole right here to the right of aluminum? Mendeleev predicted that an element that was similar to aluminum existed, but had not yet been discovered. He called it Eka aluminum. When gallium was discovered a few years later, Mendeleev's predictions about the element's properties proved to be remarkably accurate. In short, the periodic table is more than just a table. It's one of the most useful tools in a chemist's repertoire. It is a masterpiece of data visualization, and its incredible design clearly shows the groups and trends among 118 different elements. Rest assured, its brilliant architecture already has a home prepared for each element that remains as of yet undiscovered. Thanks for watching, and make sure to check out the other videos in this series.
You're welcome. We will watch. All right, so here are our patterns. So what do you call the law stating that elements, when listed in order of their atomic numbers, originally atomic weights, fall into recurring groups so that elements with similar properties occur at regular intervals? Caden.
Period.
Yeah, periodic law. Oops, sorry. There you go. Periodic law. All right. So this is where Mendeleev came in, and this is where Moseley finished up. So an electron of an atom located in the outermost shell, valence shell of an electron, can be transferred to or shared with another atom. What do we call these electrons, Liam?
Valence.
These are our valence electrons. All right. And what do you call the name of the horizontal rows? These are the periods. Okay. So if you look at the periods, it gives you an idea. If you look at the numbers, like this one doesn't have the numbers above it, but like the one you used today in lab had numbers above it. And it can give you an idea of how many valence electrons you have. So for example, if you look right on this one right here, how many valence electrons did it say the noble gases had? They don't interact, so their shell is full. Remember? 8. 8. Okay. So you see that number there? 8. How many electrons do you want in a shell, in this shell, so that you're not interacting with anything? Do you know? 8. 8's what you want. Okay. So because it's 8, now I want you to notice this you should be able to recognize pretty quickly. Name me one of the salts. How about this? What was the salt that was your unknown? Remember, it wasn't a sulfide, it was a salt, it was a chloride. Do you remember what it was, what your unknown was? It wasn't strontium, but that was a good guess because it was a nice bright color. Does anybody know what it was? Do you know? It was lithium. All right, Colin gets it. So it was lithium chloride. So look, find lithium on the periodic table. How many electrons in its valence shell? 1. How many electrons in chlorine's valence shell? 7. How many electrons does a little atom want to be happy? 8. So you're going to get lithium chloride. How about sodium chloride, potassium chloride? These are all ones you used last week. They're happy because now they don't have one very high energy, one over here, one very low energy, one over here. They slap them together. They have a nice complete shell. Everybody's happy. Now we're not interacting with anything. We're chill. We're cool. We can just live on our own and not be volatile, right? So that's why you very often are going to find salts composed of these guys and these guys. They go together all the time. You'll see them in lab this year dozens of times. We'll deal with those. All right. So again, you've got valence electrons in each group. Here, show your numbers: 1, 2, 3, 4, 5, 6, 7, and 8. And you can tell what will go with what. How about a 6 and a 2? Will that give us 8 and make us happy? So a 6 might be nitrogen, and what might be a 2? Yeah, maybe. Yeah. But you'll find, oh no, not nitrogen, oxygen, sorry. That's a 6. 6, not nitrogen. So you might find oxygen. One of these guys. You'll see them going together more often. All right. So you've got your groups and your periods. Your groups are your columns. Remember, columns are the things that are on a porch like this. They're vertical. Your rows are like you go into a theater. What row are you in? How many rows from the screen are you? So those are your periods. So rows are periods, columns are groups. So you have main elements, and then this chunk in the middle is called transition metals, and then we pull out of transition metals and we get the lanthanides and actinides, and these are your biggest main chunks of elements. But the different tables you look at are going to have them labeled in all sorts of ways. As you see, this one has lots of different labels. You've got your transition metals here, but it's also taken your main group elements on this side and on this side and divided them up. You've got alkali earth metals here, and alkali earth metals, alkali metals, and then what are these guys? Does anybody remember what these guys were from last year? We talked about them on the diagonal there. Do you remember? Metalloids. And what were metalloids good for? Does anybody remember what metalloids were? Semiconductors. Yes, your semiconductors are metalloids. There you go. So you can see that this is the most basic way to chunk it up, but it can be chunked up in various different ways. So you also can, these blocks have names. So we saw them right here. Here they are again, but they're named S block, D block, P block, and F block. Okay, yet another way to organize it. And then here's one that has tons of information. So this one's very similar to the one we have here, right? You can see how detailed this is. So again, this one has our metalloids here in yellow. And everybody's noticed right here, right? I hope. So right here, this one is purple over there. It's what? Blue. But this little block is all these, right? And this little block is all these. Now, there is, you can find it online if it helps you visualize, but there is a way that you can make it out of paper, and it's like a cylinder, because really what's happening is the patterns are repeating. You got the lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and then it goes back. Like sodium is really the next thing after you pass neon. It looks like you're starting over, but you're not. It's a continuation. It's just that this is like a 2D thing, right? There's a way to make a 3D one out of paper that might help you visualize it, but it's like a spiral kind of a cylinder, and it includes the lanthanides and actinides in a way that you can kind of visualize them a little better. So if you're crafty and you like origami, so you have your main group again, right? And then you have alkali metals and alkali earth metals, and then halogens, and then your noble gases. Remember, our noble gases are important because they don't react with things. They're what we call inert. They chill on their own. And then this dude is by himself, right? Hydrogen is, yeah, there we go. Hydrogen's alone because it doesn't really fall into any of the other groups. It doesn't, the properties are not such that it fits with the others. He's just kind of all by himself up there. He's also got no neutron. He's real lonely, but he's like, you know, he's one of the most common elements in the entire solar system, right? What's going on in the sun? What's powering the sun? Does anybody remember? Do you remember, Jordan?
Hydrogen forming with other atoms, right?
Yeah, you're close. You're close. Drew?
It's the hydrogen when it gets put under the immense pressure
Uh-huh.
from gravity. It fuses together, turning into helium.
There you go. It's nuclear fusion going on in the sun. That's what's powering the sun. And you're getting hydrogen. Yeah, there's an immense amount of gravity because the sun is huge. And this is what happens in stars. But it's pulling all those hydrogen atoms together and they are combining to form helium, which is nuclear fusion, or the joining of two atoms together. So most of your elements are metals. Everything in red is a metal. And you may not be thinking of metals. When you think of metals, you probably think of like, you know, what the arms on the folding chairs are composed of, or like, you know, yeah, metal. You probably think of the arms on the fan or whatever. But sodium is a metal. Potassium is a metal. You know, and magnesium is a metal. A lot of these are vitamins too. Do you need sodium to live?
Yes.
Yeah. Do you need magnesium and potassium? Oh yeah. These are hugely important. In biology, what makes a lot of your nervous system and musculature function are sodium and potassium channels. And if you look, you can see that they are very chemically similar because they are right next to each other on the table. Mm-hmm.
My muscles twitch because I don't get enough magnesium.
Oh, there you go. Yeah, if you don't twitch, I mean, your muscles twitch if you don't get enough magnesium. So I have a weird thing. I don't know if anybody else has ever experienced this weird thing, but I cannot eat bananas after dinner because they're full of potassium, which is great because it means I don't get leg cramps at night, which I can get, but I don't sleep well because potassium is like, keeps your brain activated. And I dream like a crazy person. And they're either nightmares or they're disturbing or they're really vivid. And like a month ago, I don't know, I had something with I put a banana on my ice cream. I was like, I really just want a banana before. And I sat there and thought, don't do it, stupid. You know what's going to happen. And the whole night I was like, oh my gosh, what am I dreaming? I mean, like, it's like a fever dream, but it's not. So yeah, a lot of these metals, straight up metals that you eat, you know, that are part of what make up your body. Metals aren't necessarily how you think of metals traditionally. So your transition metals, the properties of the transition metals are similar to each other. They're very different to the properties of the main group metals. So these have high melting points, high densities, moderate to very hard. These are what you think of really when you think of metal. Like if you envision a metal, y'all right back there? These are kind of what you think of. So in general, transition metals have 2 valence electrons, and we're filling d orbitals in the shell below the valence. So la la la. So our actinides and lanthanides, these guys at the bottom, like, why are they down here? What are they? So they're found in actinides. So actinides are found in your actinide series. There they are. They're from 89 to 103. The actinide series is in the F block, right? We showed that. They're radioactive. All the actinides. So all these guys right here that are pink, these are all your radioactive. Colin and Drew, do I need to play a part? Seriously. These are all the radioactive elements. Do you need to like take a walk? Oh my God. So they have maximum of +6 oxidation, which we haven't gotten to yet. And the valence electrons are in the 5f orbital. Now your lanthanides above it, the ones that are purple over here on this chart and green on the TV, these are 57 to 71. They're in the F block again. They're not radioactive except promethium. Where's promethium? It's right here. It's PM. He's radioactive. This one, but none of the others are. They have a maximum +4 oxidation. Again, we haven't gotten oxidation yet. And their valence electrons are in 4f. Obviously, those are 4f. If the ones beneath it are 5f. All right. So looking at your notes, let's see if we can get some answers to some of these. Why do lithium, sodium, potassium, rubidium, and francium all react with chlorine in a 1-to-1 ratio? Caitlin.
I just put the reason why they're all the same.
Okay, what'd you put?
They're all white solids that dissolve in water to form solutions that conduct electricity.
Okay, that's a good answer. Anybody else have a different answer? Okay, be sure that you have, whoop, am I clicking away? Be sure that you have this answer. They're all in the same group, meaning they have similar chemical properties and similar in the way they react to things. Now, remember I was just telling you, these dudes over here have 7. These dudes over here have 1. They want 8. So that's why they're all interacting with each other. They all have one valence electron, and chlorine has 7 valence electrons. So that's why they're interacting. All right, how did Newlands organize his elements? What was his method? Who's got it? Colin.
In order.
In atomic mass. Okay. So he based them on atomic mass and he grouped them into octaves. Remember, groups of 8 based on similar properties. So what method did Mendeleev use when he put his table together? Okay, Xander.
He organized it by atomic mass.
Yep, he used it by atomic mass from left to right. All right, so he got rid of the octaves and said, let's just go left to right with mass. All right, so what did why did Mendeleev have gaps in his table and how to use the gaps? Addie? Yes. Yes, they just hadn't been discovered. So he used them pretty much to prove, like, if anybody finds these, they're going to prove I'm right. That was the genius of Mendeleev's thing, that he had these blanks where he's like, there's something missing here. And I know there is because for the pattern to repeat, this element has to have the following characteristics. And we don't know one yet with these characteristics. It's going right here. And he's been proven right many times. Gallium being the first one. I actually have some gallium upstairs and it's in a syringe because it's a metal, but it's literally, it's like they said, it's melting temperature and melting point is super low. You can squirt it in your hand and chase it around. And it's not like mercury that's toxic. If you put it in a little cup, it'll make a ball and you can just roll it all around and it's metal. It's just super low melting point. Yes, it actually grows like, looks like hair. It's interesting. So what was Mosley's contribution to the table? Jordan?
He switched from atomic mass to atomic number.
Yes, yes. Atomic number over atomic mass. So let's look at the number of protons rather than the mass, which was important because we have isotopes and that'll mess up your pattern a little bit, somewhat. So why was Mosley able to resolve the discrepancies in Mendeleev's table when Mendeleev could not? Caitlin?
Because of his X-ray.
Yeah, his X-ray spectroscopy. So allowed him to determine the number of protons in each element and thus their atomic numbers. He was able to say, all right, this is the exact number of protons. So now we can give it a number and now we can put it in order. So why are valence electrons important? PJ.
Because they're the ones that interact with the other atoms.
Yeah, these are the ones that interact. Doesn't matter what your lowest energy level of electrons are doing unless they're also the same as your higher energy level of electrons. That matters. But if you have ones that are higher in shells further and further out, those are the ones that are interacting. So why do elements with similar properties appear at regular intervals in the periodic table? Asher. Yeah, so your periodic law states that when elements are arranged in order of increasing atomic mass, there's periodic repetition in their chemical and physical properties. And that's because as you add 1 proton each time, you tend to add 1 electron each time, and the electrons are what's doing the interacting. So how is the electron configuration similar for each element in a group? Jordan?
The number of valence electrons are the same.
There you go. Yeah. So same number of valence electrons. Why does that say dame? Oh, okay. I'll have to fix that one there. So how is the electron configuration similar for each element in a period? Colin?
The same number of energy levels.
Yeah, the same number of energy levels are filled. Exactly. The same number of energy levels are filled. All right. So next week, y'all are going to get out a little early today. Next week is fall break. That means this. Do not show up here. I will be in my pajamas when I enter the door. You don't want to see that. You'll go, because that will still be, yeah, it'll be bedhead. Even at 1:30 probably or whatever, if you were to skip lab. I'm chilling. Okay. So don't show up here. But it's almost October. So what's that mean? Say it loud again. Tinker Day, what the heck are we talking about? All right, somebody, you got to prepare for the donuts, Krispy Kreme donuts. If you can't have them for some reason, let me know. All right, now there's a whole bunch of new people here who are confused as all heck. Who would like to explain to the newbies why we are excited about October coming? Who wants that? Ridley? Okay, eyes on Ridley.
Cause Tinker Day,
Okay, what in the world? Shh, that's that. What is Tinker Day, Ridley?
when you go climb a mountain in funky outfits and then eat donuts.
What are we talking about? Clear? All you new people? They still look confused. We have to help them out. All right, somebody elaborate a little more. Asher's got it. Asher?
You get credit by eating your donuts, climbing a mountain, and or taking a picture of yourself in a odd costume.
Why are we doing this? Somebody explain. Good one. All right, Drew, why are we doing this?
College number one, go to Holland University, they have this thing where every year the
School president.
school president basically wakes up in a day during the month of October and says, all right, they take your day. And basically there's like no class, you just like walking down like the cafeteria and you, yeah, why are you staring in my soul? And they like have donuts and you climb Tinker Mountain.
Mmm.
Like climb a little mountain.
Yes, so here's how it works. All right, so my college, my alma mater, Hollins College in Roanoke, Virginia, little tiny women's college, founded in 1842. In the 1890s, they started this tradition. So one day in October, we don't know when the day is. One day in October, the president of the college decides, I shall declare this day Tinker Day. Everybody on campus is awakened by the chapel bells ringing, which are big, loud. I was the person that got to do the ringing my senior year. So I was the first student to know that it was Tinker Day my senior year. It was a big honor. I was super psyched. These are bells that are like, the rope's like this big, and you have to kind of start like this. And then when you get going, you just you hold on and your feet come off the floor and you go with the rope because the bells are super heavy. So you're flying up and down. It's a whole Quasimodo thing. In my pajamas, I have a picture to prove it. In my pajamas, my slippers. Woo, right? All right. The whole campus wakes up because it says ding, 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 ding at 6 a.m. Ding, 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 ding. And you know, okay, today's the day. So you don't even change your clothes because it's a women's college. So who cares? And you wear your jammies and you march down to the cafeteria. Everybody does it. You get to the cafeteria and they've got regular breakfast plus Krispy Kreme. All the thousands of Krispy Kreme donuts, all the Krispy Kreme you can imagine eating. So you eat your breakfast. Then you go back to your dorm or your apartment or your house. And you get changed, but you've been preparing for months. You've been preparing since like the first day of school. You've hit every thrift store in Roanoke. You brought stuff from home. You've been crafting things because your task is to wear the most ridiculous thing you can wear. So you go back to your dorm and you change. And then after that, everybody meets on the front quad and the president comes out and she reads this proclamation that's read every year and declares it Tinker Day, and there's no class. And then everybody, from the guy that mows the lawn to the college president and all the students with their wacky costumes on, walk from the campus down this little road, down this other little road, and up Tinker Mountain. Everybody hikes up. They've been doing this since the 1890s. Imagine what you wore in the 1890s, the shoes you wore, the long full-length wool skirts that you wore. Hike the mountain. So the women hike the mountain, they get to the top, they do skits, they sing songs, and then they feed us fried chicken and Tinker cake every year. And then it's over and you have to wait a whole other year for the most amazing day of the year. Now, alumni get the privilege of hosting local parties. So last year I was like, you know, I think I'll do it. So I hosted the North Atlanta area Tinker Day party, and I'm hosting it again this year. So every single alumna from my college is invited. So if you're in the area and you want to come about a Tinker Day party, come to a Tinker Day party. So we had fried chicken, we had Tinker cake, we had Krispy Kreme donuts. So I'm doing it again this year. I think it's October 6th. Anyway, or whatever that is. I think it's 6th. So in the back. So here's why it's important to you. All right. This is why it matters, because it's an opportunity for extra credit on your midterm, on your final midterm grade. I tack points right on top of it. Your midterms are 10% of your grade. You for sure want the best midterm grade you can get. So here's how you get extra credit points. If Tinker Day falls on a day other than a Tuesday, you're going to post a picture in the forum. Now you will know it will not pacify anyone that it's Tinker Day because I lose my mind and I tell the whole world. Okay, so there will be a post in the forum. It's Tinker Day! And you will know, and I will send out an announcement through Teacheries. Everybody will get it. It'll be 6:30 in the morning. You'll know it's Tinker Day. You'll be like, oh my gosh, looking at your phone first. This woman's excited because I'm excited because it's Tinker Day. All right, so you will know. There will be a post in the forum that says, Happy Tinker Day. Your job, should you wish to accept it, is to post a picture in the forum of either you eating a Krispy Kreme, you taking a hike, or you wearing a wacky day outfit, or you wearing green and gold. All right, those are my school colors. If you do that, you can get 1 point. Now, if you take a picture of yourself on top of a mountain, eating a Krispy Kreme, wearing something wacky that also happens to be green and gold, and you can prove that you took that picture on Tinker Day, like take mom's phone and hold it up that says the date on it, whatever you do, back when we used to use newspapers, that's 3 points on your midterm. You can't post an old photo. You can't take the picture 3 weeks in advance and be like, I'm going to pretend it's, no, you got to do it on that day if you want 3 points. Now, you have to post it on Tinker Day in the forum. Now, if Tinker Day falls on a Tuesday, this makes your life easier. If you wear something green and gold to class, it's 1 point. But if you wear something green, it should say if you wear something green, gold, and wacky to class, then it's 30 points. So if you come in a crazy outfit that happens to be green and gold, you get you some 3 points. Drew?
What classifies the mountain?
Oh, well, the mountains around here would be Kennesaw Mountain, Sawney Mountain. Those are your nearby ones that are mountains. Like, you can't go up the hill at the park. Well, if that's the closest thing you've got and you make an effort and you climb 20 feet up a hill and take a picture, be like, look, I climbed a hill. I'm probably going to give you credit because I really want to give you the credit. I really want you to get, but.
I climbed the hill in this wacky outfit.
No, that.
Children are staring.
Yeah. You're like, why are they looking at me?
So
Yeah. So here's the thing to remember. When you come in, whatever Tuesday falls either on Tinker Day or after Tinker Day, you will arrive to donuts. You will get Krispy Kreme. So if for some reason you can't eat Krispy Kreme, let me know. Yes, Lucas.
What if you put this to the mountain on your bed and then it's climbing bed?
Say it again.
What if you put this to the mountain on your
That
bed?
will not count. You have to make an effort.
Okay,
Look.
Yeah.
Here, I'll show you why you have to make an effort. You have to make an effort to honor people like these ladies right here. Look at what they're wearing. This is 1890s climbing the mountain. Look what she's wearing. Both of them. Look what they're wearing. I dare any of you. Come on. These are tough women, right? So these are pictures throughout history. Yeah, they're all going together. What's the point of this? The point of this is you're talking about a women's college founding in the 1800s when women were still at a great disadvantage in many areas, right? And Hollins was a school that will, like, the motto at the time, or not the motto really, but the thought was that women deserve the same rigorous level of education as men. And part of that is psychologically, can I conquer things? Can I conquer the world? So these women in their little, leather shoes and woolen skirts conquered the mountain. And that's the whole point. Colin.
Credit points would it be if you take a picture of yourself on top of a mountain eating a Krispy Kreme donut, wearing a dress like that?
That would count as a wacky outfit. But make it green and gold and then you get I mean, look at what she's got on. Like, she's not playing. Yeah.
Is it more,
Wait a minute. Andrew's asking a question.
is it more points if it's a green and gold Wolverine dress?
Oh, that would be pretty amazing. Three is your max in either case.
Challenge accepted.
Hey, all right. So anyway, if you want to see the kinds of things people have worn in the past, all you got to do is go over to YouTube and put in Tinker Day and it will be there. And it will be, I mean, I have a picture of two good friends of mine. One of them was on crutches, but they had dressed as Tweedledum and Tweedledee and they were standing side by side and one of them's on crutches. And I have another girl I was in class with who for 3 years went in a yellow princess gown and hiked the mountain in a yellow princess gown. There's always the college president has a green and gold tutu that stands out like this. And that's what she wears on Tinker Day every year. But the most fun was my second year there. We got a new president, Janet Rasmussen, and she brought along her husband, who was this giant Nordic man named Ulf Rasmussen. And Ulf freaking loved living on a women's college campus and being like the dude that everybody was like, yo, Ulf, he'd be like,
Hi.
right?
Hi.
You know, but he wore every single day a Viking helmet.
Oh, yeah.
The horse, the first single day he came out in it, we were all like, he's for real. He's a real Viking. Like, it was great fun.
I can know what you'll actually have points though.
Oh, that's what I tell you. So anyway, it's fun. It's my favorite holiday, and I love it. And I like to share the tradition with you guys and pass it down. Like over here, you notice this is where I put my stickers for the colleges that you guys go to. Anybody that goes can bring me one. There's a Hollins one over here. That's a Krispy Kreme donut. It's the shape of a donut, right? So, yeah. So anybody have any questions about that? Do not come here next week. I love you, but do not come here.
Aw.
Stay away. Chicken hexing you all. All right, if your ride's here, you can split early, or if you drove yourself, you're fine. All right, and otherwise, just hang till it's time to go. Put these out on the counter. I'll find you some Tinker Day videos to marvel at.
Wait, why is it so secret?
That's always been. You know how many people call the Krispy Kreme that like every night in October and be like, I'm just checking in tomorrow's large order for Hollins just to see if anybody goes, yeah, sure, we're getting it ready. You can put it up there in the folder
Krispy Kreme even
if it's
existed in
done.
1895?
No, that got added in later years.
I didn't understand Tinker Day last year, but now I get it.
It's great, isn't it?
Great.
It's the most fun thing ever.
And then the next time we're in it.
No, absolutely not. Hey, we're all gonna-
Yeah, we're off on. We're off on the 24th, and we're back on the 1st, October 1st. You're gonna be 16, yeah.